All right, this is parent functions and transformations that we're going to be talking about today. What's going to happen is you're going to have four different parent graphs that you're going to be referencing. One of them is your constant function when y, or f of x in this case, equals a constant such as 1. This is the parent function, so it could equal any constant. Doesn't matter whether it's a whole number, integer, fraction, decimal, it's fine. Your domain's all real numbers. Your range is simply the value that it was. By the way, it'll always be a horizontal line. You've also got your linear function. You'll think of mx plus b a lot of times, or ax plus b. Slope-intercept form is usually how this is presented. This is the parent function, though, where your slope is 1 and your y-intercept is 0. Both domain and range have all real numbers. All right, this is your absolute value function. This is read f of x equals absolute value of x, meaning how far away is x from 0. So that's the reason why the y values are only positive. Distance is positive. So you're all real numbers for your domain still, but your y is greater than or equal to 0 because it can't be negative, because distance can never be negative. Quadratic, f of x equals x squared. This was practiced a lot in Math 1. Your domain is still all real numbers, and your range is also y is greater than or equal to 0. This is called a parabola on this last one here. All right, now moving into example 1, what we're going to do here is we're going to identify the family that this function belongs to and compare it to its parent function. So we're going to describe it as a transformation. Now, what's going on here is we're going to see that there's an absolute value inside the function. Also, the shape is a v. V for value is how I always say to remember it. So this is going to reference back to absolute value function. So that's going to be my first answer. It's in the absolute value family. Now, how does this one compare to the parent function? Now, the first thing that's going to stand out to me is that it's going to be multiplied by 2. So this is actually more narrow than what the parent function was, because the parent function is actually getting multiplied by 1. 1 times the absolute value of x. So what that tells me here is that this has been stretched vertically by a scale factor of 2. Now, there is one other transformation that's happened here. On the original parent function, I'm going to slide back up to it one last time. You're going to see that it's actually at 0, 0 is where everything starts. This one's actually at 0, 1, and that's because of the plus 1 at the end. So it's been translated up by 1 unit. All right, there's my entire answer. All right, so on the second example, we're going to identify the parent function. It says graph the function and its parent function. Now, I've already graphed the function here by typing in x minus 4 into my Desmos, North Carolina calculator. And the parent function would actually be y equals x, because this is linear. So the blue one's my parent function. So there's actually two different ways I could describe this transformation. Here's how I'm going to think of it. Since it was subtracted by 4, that means every y value got 4 units taken away from it. So this translated down 4 units. So translated down 4 units. And if it had been plus 4, it would have been going up instead. Now, describing the domain and range is really easy. For any linear function, your domain and range will always be all real numbers. Because the x and y can be any value L. There's no restrictions here. then that wraps that problem. All right, so on example 3, I'm going to be asked to graph negative x squared. I've already done so. Now I'm going to also graph its parent function. Now since this is quadratic, my parent function is y equals x squared. So the green one is my new function, the blue one is the original. This has not been moved up, down, left, or right. The vertex is actually still at 0, 0. What's happened though is it's been flipped, or what we say in math is going to be reflected. It has been reflected in the x-axis. This is my line of reflection right there. So that's my answer for the transformation, reflected in the x-axis. And what I'm going to say for the domain and range is that my domain will again be all real numbers. You aren't going to see anything other than that for right now. I'll point out whenever things are going to be changing there. And for my range though, for my parent function, the y values could be anything greater than or equal to 0. But for my new function, the y values can be anything less than or equal to 0 because it's going down from the origin. Now technically I've actually made a mistake here because it was p of x. I shouldn't be using y here. Should be p of x is less than or equal to 0. Not a huge deal, not something that I'm going to necessarily count off a lot for, but it is important to notice. Alright, so more of the same on example 4. What's going to happen here, I've got 2 times the absolute value of x. Yet again, this is the red one is the new function. The black one is the parent graph of absolute value of x. So it's not been moved left or right, up or down. What's actually happened here is that it's actually just been stretched vertically by a factor of 2. Anytime that it's getting multiplied by a number greater than 1, it's going to be stretched vertically by that number. Okay? So, stretched vertically by a factor of 2. Now, I wasn't asked for domain and range, so I'm going to move on to the next one. So what's going to happen on this next one, y equals 1/2 x squared, well, h of x. So I've already thrown that in, that's the blue graph. The green graph represents x squared, the parent graph. And what I'm going to say here is that it's again not been moved left, right, up, or down. It's actually been compressed vertically. And the reason why I'm going to say compressed is because the a value is less than 1. So if your a value is less than 1, it's been compressed. If it's greater than 1, it's been stretched. So it's going to be compressed vertically by a factor of 1/2. But it's important to know when it's greater than 1, it's stretched. When it's less than 1, it's compressed. All right, on this very last example that I've got for you here, I've actually got 3 transformations happening. There's actually quite a bit going on here. So I'm going to go ahead and show the graph of it and the graph of its original function. So what I'm going to point out here is, first of all, it has been reflected because the new graph is actually opening down. The parent function, absolute value of x, is opening up. So I am going to go ahead and write in one of the transformations is that it has been reflected in the x-axis. And what gives that away when I'm looking at it is the fact that the graph's been negated, is what tells me this. All right, it's also been moved left, right, up, and down. I'm going to tap on this new point of inflection here, this change in direction. It's at -5, -3. So the x value is -5. That tells me it's been moved left 5 units. I actually call that translated. Translated left 5 units. And it has also been moved, in this case, down 3 units. All right, time for my domain and range, and I'll be done. For my domain, it is yet again all real numbers. Just assume that's going to be the case until I tell you that it is no longer the case. You're not going to see anything other than all real numbers for the time being. We will get to something that is different. So range is what's different here. For the parent graph, it is greater than or equal to 0 because it went up from there. Here it's going down from -3. So you always look at your y value. So g of x, technically not y, because this function was supposed to be g of x. G of x is less than or equal to -3. That is, the -3 represents the highest value g of x could ever be. All right, that's a wrap. Thank you.